Hi, I'm Chris Broyles. I work at the Storm Prediction Center here in Norman, Oklahoma. Over the last 3 years, I've been working on the Tornado Genesis project with a team of 8. We've looked at 208 storms that produce strong to violent tornadoes. During the project, we developed an animation. The animation shows the storm that moved through Moore, Oklahoma on May 20th, 2013 and produced the EF5 tornado. The animation shows the storm as it develops from a cloud to a supercell, and then it shows how the mesocyclone produced the tornado. You're going to see the complete life cycle of the storm. I hope you enjoy it. Well, I want everybody to know that this is a joint project between the Storm Prediction Center, the National Severe Storms Laboratory, University of Oklahoma, and the Weather Prediction Center. Okay, we're going to look at the animation now. We're looking to the north-northwest. We're at 15,000 feet. And as the storm develops, the helicopter view will turn more toward the west gradually. And then we will see the storm increase and then become more organized. And then it will become a supercell. And then it will come and approach us. And then the tornado will form. And we'll see the tornado and the whole life cycle of the tornado. In the upper right side of the screen, you'll see the radar images. Things like wind speeds associated with the tornado that were estimated. We'll see a pressure trace that shows how the pressure fluctuated within the tornado. And we'll see how the 700 millibar wind speeds increased and how that was associated with tornado development. So I'm going to show you the animation one time, and we're going to just look at it, just enjoy it for the first time, and then we'll go through again, and then I'll show you the different processes that happen within the animation. So we're 90 minutes before the tornado. The Moore storm will develop to the left side of the screen. On the horizon there's the Moore storm. It's just a cloud, and it develops an anvil which spreads off to our right. Then there are some towers that develop on the flanking line. That's what it's called, the flanking line of the supercell. And then we can see the mesocyclone there. And then some cells that merged into the supercell, which caused a surge underneath the mesocyclone. The tornado forms right there. And so the last surge comes and causes the tornado to dissipate. All right, we're going to look at this animation a second time, and I'm going to show you the different things that happened that contributed to the formation and development of the tornado. The Moore storm became a cloud about an hour and 10 minutes before the tornado. And that updraft grew quickly and then developed an anvil, which spread toward the northeast. And then we saw some cells that develop along the flanking line there. And then the mesocyclone forms. And so supercells are storms that have an area of strong rotation within the updraft. And you can see that there. And that strong rotation gradually will descend toward the low levels. And in the Moore supercell case, 2 cells developed behind the flanking line and developed downdrafts. These cells, you can see the lines that form there, those are downdrafts associated with those cells, and they merge together. And from that cell merger, it's what we call a cell merger, when 2 storms, these are 2 smaller storms, that they came together. And the outflow from those cells surges underneath the Moore flanking line and then creates this surge that goes underneath the mesocyclone. We call this the rear flank downdraft surge. It comes from the cell merger. And the RFD surge, these generally precede tornadoes. And so another thing I want you to notice is that the surge goes toward the area to the right of the mesocyclone there, and it creates this corridor where winds are channeled. This channeling is called the inflow channel. And so this is important to the formation of the tornado, because the air that is coming into the updraft of the storm must go through this small channel, but air is rising quickly through the mesocyclone, and so what happens is that not enough air can get down toward the surface, not enough air can get into the circulation, and so more air is evacuated out the updraft, and then so there's a strong surface low, an area of low pressure that develops underneath the mesocyclone, and because the inflow channel forms, that surface low really deepens quickly. And so that's one thing that contributes to tornado formation. But if we also go back to look at the cell merger here, this did cause the RFD surge, the riffling downdraft surge, as we talked about. But it also has a core of precipitation, of rainfall and wind that comes down through the flanking line, and that is called a descending reflectivity core. In meteorology terms, it's called a DRC for short. And so this was the first DRC that impacted the Moore storm. And so this area of precipitation and wind comes down and hits the surface right here, and then as it hits the center of the rotation, that's when the tornado formed. So this DRC was important to tornado formation for the Moore tornado. And if we look at the lower right-hand insert here, we can see that the DRC is in the lighter gray on the left side of the insert, on the lower right of your image. And then there's a darker set of lines there, and that is air and precipitation that is being pulled around the mesocyclone due to the descending reflectivity core. And that area of darker lines is called the occlusion downdraft. Notice that right here, we're just over 30 seconds away from the tornado beginning. And notice how the descending reflectivity core and the occlusion downdraft, these lines, there's 6 lines here, they're all concentrated down within the lowest 200 feet, right in front of the tornado. And so what that does is it really increases rotation at the surface. And so when a tornado develops, as in the Moore case, the tornado really develops at the ground first. So the question was, why does the funnel drop? Well, if you notice that the funnel drops right along the leading edge of that wedge of air. And so in a case like the Moore storm, the tornado really develops at the surface, but also develops like all the way up through the mesocyclone really quickly. And so that descending reflectivity core was very important. Also notice how the winds, as the tornado develops, there appears to be like this stretching where the winds, the lines that represent the winds kind of separate. And the tornado becomes very large very quickly, and the Moore tornado developed to over a mile wide within the first 10 minutes. And this is at the time when the Moore tornado was 1.1 miles wide. It had reached maximum width at this point. Another thing I want to point out is that as the inflow channel formed over here in the insert, also there's this area of rotation that's horizontally oriented. It develops and then moves around the western side of the mesocyclone, and we call that the streamwise vorticity current. This is a feature that has been studied over the last 15 years, and we are starting to understand more about it. It helps contribute to the strengthening of the mesocyclone, which then also helps maintain the tornado. Another thing I want to point out over here on the left is a cluster of cells that move in toward the flanking line. And this cluster of storms caused an outflow boundary to move across in front of the tornado, which you'll see at the bottom hand of the image. And it caused the inflow channel to be very long. But also there was a second impact that was made, a downdraft core of precipitation. This is the second one, merged into the flanking line, which we see right here. And then it descends to the ground, and then wraps around the surface circulation around the tornado. Well, look what happened when it did that. So the surface circulation then rapidly expands as the second DRC wraps around the tornado, and this is like a skater pushing their arms out, which then causes the rotation to slow down. And then when they pull their arms in, the rotation rapidly quickens, and then that's when the tornado developed to maximum intensity. And at this point, the tornado is at EF5. It's almost a mile wide. When you consider those two things, this was when the tornado was at its strongest point. One other thing I want to point out is that when the second descending reflectivity core right here, look how it caused another surge to come around. This is the second RFD surge. And then we get these boundary layer vortices. And these are called gustonados. They're not tornadoes. The circulations form along the rear flank downdraft boundary. The rear flank downdraft is the area that's behind this curved line which extends around the tornado. And so the rear flank downdraft is this area that's underneath the flanking line and where the tornado is up into where this curved line is. And the inflow region of the storm is this area on the very bottom of the picture, and then that wraps around into the inflow channel. And so notice how the RFD surged there. And then another thing within the rear flank downdraft that we see around the tornado are these spiral bands. If we look at the insert to the right and the radar image up just above that image, right here you can see the spiral bands that form around the tornado. And it's a little bit, they look like a hurricane, but this is actually related to the ejection of debris from the tornado. And so notice how the spiral bands are drawn in around the tornado in the animation. And then one thing we want to look at here is that at this time, the end of the 700 millibar jet, which we see to the left, is approaching and then passes. And so notice on the track here at the top of the image, how the tornado jogged to the left and then jogged to the right. It went more northeast and then turned southeast. But then as the winds that were impacting the storm weakened, the third surge of air came from upper levels, which was more cold and stable. And then when it hit the circulation, the tornado weakened. And so that's how the tornado on the Moore day developed and intensified and then dissipated. We're going to take a look at the animation one more time. This animation was done to continue the strong history within the weather community of making thunderstorm schematics, supercell schematics. And this was done because I wanted to be able to show how tornadoes form and communicate that to people that may be meteorologists but may not be meteorologists.